So far, we have been studying infinite series where every term is a real number. In this lesson, we shall be talking about infinite series where every term is a function, in particular real valued function on a particular domain. Before we start our discussion, please make sure that you have already studied infinite series of real numbers and the difference between pointwise and uniform convergence of a sequence of functions. Let us start with the following definition. So here, you get a sequence of real valued functions. They have a common domain, x. Now here, x can be any kind of set, as long as the values of each one of these are real numbers. Alright, so by an infinite series of functions, we mean simply just an infinite series where every term is a function with a common domain. Since the elements of the series are the terms in the series are functions, then its convergence will have two different types or two different modes, the pointwise and uniform convergence. So here, we say that this infinite series of functions converge pointwise to a function s with a domain x as well if the sequence of partial sums as a sequence of functions converges pointwise to s. Again, the word pointwise means that for every point x in the domain x, Sn of x as a sequence of real numbers should converge to the value s of x. In the case where s of n converges pointwise to s, we write this notation, and in case that this sequence happens to further converge uniformly to s on x, remember, uniform convergence is a stronger form of convergence. If it happens that this sequence converges uniformly to the function s, we say that the series converges uniformly to s on x. Sometimes we also use this equation and indicate the word uniform to mean that the convergence is uniform. Let's look at some example. Let f sub n of x be the function x raised to n minus 1. Now if I write the summation of x raised to n minus 1 and from 1 to infinity, I get this infinite series of powers of x. Now, as you can notice, this infinite series is just an infinite geometric series with a common ratio x. Hence, from our knowledge of infinite series, we know that this series will converge to the sum 1 over 1 minus x whenever the common ratio x has an absolute value less than 1. In other words, x is between -1 and 1. Hence, if we let x be the open interval from -1 to 1, including all the points that are described here, and if we let s of x be the function 1 over 1 minus x for x in x, then we can say that this series of functions, summation of f and n from 1 to infinity, has a sum s, and the convergence is pointwise on x. At this point, we would like to ask if the series converges uniformly to s. Now we claim the following. We claim that the infinite series converges uniformly on the closed interval from -r to r for all r between 0 and 1. However, the same series does not converge uniformly on the entire domain x. Meaning to say, the uniform convergence of an infinite series, just like the uniform convergence of a sequence, depends also on the domain of discussion. If I may draw the diagram for you, the domain of convergence is the open interval from -1 to 1, meaning to say at all points in this open interval, the convergence is guaranteed, and the equality here is guaranteed outside this interval, the equality may not hold because this infinite series may actually diverges. What we're saying here is that if you're going to look at the interval, no, from around 0, the closed interval from minus r to r, where r is between 0 and 1, then it can be guaranteed that in this interval the convergence is uniform. However, on the entire interval, the convergence can be confirmed to be not uniform. In order to show this, let's consider the sequence of partial sums. Let's consider the sequence S sub n, which is defined as the sum of f sub 1 up to f sub n. Then as you can see, for each x, Sn of x is the sum 1 plus x plus and so on plus x raised to n minus 1. Now using the identity from algebra, which is 1 minus x times 1 plus x squared plus x raised to n minus 1 equals 1 minus x to the n. Then because x is not equal to 1, this set x does not include 1 in it. So therefore, x is not 1, therefore this expression is not 0. You can divide both sides by 1 minus x and you get this equality. So if r now is any number between 0 and 1 and we construct this interval, in this interval if you take any x, then we can calculate this difference as follows. Is the difference 1 minus xn over 1 minus x minus s of x, which is 1 over 1 minus x. And doing algebraic calculation, we get the following expression as the difference. We would like to know when is this expression largest in this interval. As we can observe, this fraction is largest whenever the numerator is the largest and the denominator is the smallest, and that can be achieved whenever x is equal to r. Therefore, this expression is all less than or equal to r to the n all over 1 minus r. Take note that r is less than 1, that's why you can remove the absolute value symbol there. Hence, we can say that the infinity norm or the supremum norm of s sub n minus s as a function is r raised to n all over 1 minus r. And as n approaches infinity, we can say that this expression converges to 0. Because this norm is going to 0 from a previous lesson, we can now guarantee that s sub n converges uniformly to s on this interval. Therefore, the infinite series summation fn must converge uniformly on the interval from minus r to r. On the other hand, when you consider the entire domain x, if x is in this interval, then we can calculate this as follows. It's going to be the supremum of this over the entire interval from minus 1 to 1. But as you can see, as we keep on taking x as near as possible to 1, this expression approaches 1, while this expression approaches 0 from above. Therefore, the entire fraction gets larger and larger in value as x approaches 1. Indeed, this supremum can be achieved by taking the limit of this expression as x approaches 1 from the left, and therefore, the supremum norm of Sn minus s is infinity, and that does not converge to 0 as n approaches infinity. Hence, s sub n cannot converge uniformly to s on the open interval from minus 1 to 1. And therefore, this infinite series does not converge uniformly on the open interval from minus 1 to 1. To illustrate this in the picture, the yellow graph represents the sum s of x equals 1 over 1 minus x. The red graph in the picture is the function s1 of x, which is the constant function 1. As you can see, s sub 2 of x is 1 plus x. It's the linear function pictured in the following, When n is 3, you get a quadratic function. N is 4, you get a cubic function. N is 5, you get this polynomial function of degree 5. As you can see, as n approaches infinity, the red graph seems to approximate the yellow function better and better. The nearer x is to 0, as you can see, the approximation is better. For most of the examples, or in this example, we are lucky to know what the sum is. But in reality, or in practice, most of the times, we can only prove that the series of functions converges without getting to know what the sum is. Without really calculating the sum, we ask, can we determine if the convergence is uniform? Yes. Let's recall the following criterion due to Cauchy for uniform convergence of a sequence of functions. Recall that a sequence of real-valued functions converges uniformly on x if and only if, for every epsilon greater than 0, an n can be exhibited to exist so that the distance between fm of x and fn of x can be made as small as we wish, less than epsilon, whenever m and n are selected to be greater than or equal to n. And this must hold for all x in the domain. Hence again, the n here depends only on the epsilon, and that does not depend on the location of x. Now, for an infinite series of functions, we simply apply this criterion to the sequence of partial sums, taking note that s sub n is f sub 1 plus f sub 2 plus f sub n, and if m is greater than n, we can get s sub m minus s sub n as this is the sum f1. Because n is less than m, fn will come right here. Then here's fm minus f1 and so on up to fn. If we remove this from this sum, what we're left with is the sum from fn plus 1 up to f sub m. Hence, we have the following criterion for uniform convergence of a series of functions. This is also called as a Cauchy's criterion. To read, this infinite series said to converges uniformly on x without having to know the sum, if and only if, for every epsilon greater than 0, an n can be found so that this sum, fn plus 1 of x and so on plus fm of x, can be made less than epsilon as long as m and n are integers to be taken to be greater than or equal to n, and this must hold for all x in the domain x. Here, take note that we assume without loss of generality that m is greater than n, because if m and n are two integers, different integers greater than or equal to n, certainly one of them is bigger. So without loss of generality, in this case, we always assume that m is greater than n. Using the Cauchy's criterion, we can now state a test for uniform convergence for an infinite series of functions, which is commonly known as the Weierstrass M-test. So here, you get a sequence f sub n of real-valued functions on x. If for each n, a bound m sub n positive can be found for each of fn of x, meaning to say the function f sub n is bounded for all n on x. Okay, an upper bound is m sub n, but take note that this upper bound changes as n changes, meaning to say f sub 1 has an upper bound m1, f sub 2 has an upper bound m2, and so on. If this upper bound has a sum which forms a sum which is a convergent series, now if you add all of this upper bound and they are found to be, the sum is found to be convergent, then we can now say, or we can conclude right away, that the series converges uniformly on x. Why is this so? To prove uniform convergence, I will be using the Cauchy's criterion. So we start the proof by letting an epsilon be greater than 0. Using the fact that this series is convergent, then by the Cauchy's criterion for infinite series of numbers, you can find an n so that this sum can be made less than epsilon whenever m and n are both greater than or equal to n. Now here, I can remove the absolute value sign because each one of these m sub n is positive. Now, if we take any point x in the domain x, and if we choose two integers m and n bigger than n, so that m is greater than n, then we can calculate this absolute value using, we can estimate this absolute value using the triangle inequality as follows. It's less than or equal to the sum of the absolute values. Now, according to this property, this one is less than or equal to m sub n plus 1. This one is less than or equal to m sub n plus 2, and so on. By the manner we choose n, we can guarantee that this sum is less than epsilon. Hence, if I'm going to highlight these sentences and put them together, let epsilon be greater than 0, then there exists an n such that if x is in x and m and n are bigger than n, then this sum is less than epsilon. That constitutes the Cauchy's criterion for uniform convergence. Hence, we can now say that the infinite series summation fn converges uniformly on the set x. To illustrate the use of the Weierstrass-M test, let us consider this example. Show that the series of functions summation of cosine nx all over x squared plus n squared and from 1 to infinity converges uniformly on the entire real number line. So here we apply the Weierstrass-M test. How? First of all, we take any x in the domain, in our case is the real number line, and n, an arbitrary n. What we first do is we estimate the size of cosine of nx divided by x squared plus n squared. Taking note that the cosine function has a magnitude not exceeding 1, hence this is less than or equal to 1 over x squared plus n squared. Now take note also that if I delete x squared in this expression, the fraction will be bigger. So this is 1 over less than n squared. So in this case, this is now just dependent on n without x. So we can now call this as the upper bound m sub n. Okay? Now notice that if we add all of this mn and from 1 to infinity, we get the sum n from 1 to infinity of 1 over n squared, which is a p-series with p equal to 2 and 2 is greater than 1. Hence, this one is convergent. Since this sum converges by the Weierstrass-M test, then we can say that the infinite series n from 1 to infinity of cosine nx over x squared plus n squared converges uniformly. Easy, right? Well, at least for this example. Okay, let's proceed. Recall that if f sub n converges uniformly to f on the set x, and each fn is continuous on x, then we can guarantee, using the uniform convergence, that the limit f is 0. Is continuous, I'm so sorry. This means to say that the uniform limit of a sequence of continuous functions on a domain must be continuous. And to say continuity is an invariant property of uniform convergence. Now, if we're going to look at an infinite series of continuous functions, if each one of these f sub n is continuous on x, then we can look at the n partial sum, which is a finite sum of continuous functions. Hence, s sub n is continuous also. Now, being uniformly convergent, then we can say that s sub n converges uniformly to some function s on x. So if each one of these is continuous, by this property we can say that S is continuous as well. So sorry, napapaghalo-halo ko na yung mga terms. Hence, the uniform sum of a series of continuous functions must be continuous. So, asahan mo raw, kapag lahat ng terms ng series mo ay continuous, and you know that the series converges uniformly on a particular set, then to whatever magsasum up itong series of function na to, yung function na lalabas ay continuous pa rin. Also, we have the following property. If f sub n converges uniformly to f, each one of fn is integrable on the closed interval from ab, then we can guarantee that the uniform limit f is also integrable. Furthermore, we know that the limit of the integral is equal to the integral of the limit, meaning to say this limiting process can be interchanged. With that, applying this property to the sequence of partial sums, so if we apply this to f sub n, which we know to be equal to f sub 1 plus f sub 2, f sub n, finite sum of integrable functions is integrable. We know that this converges uniformly, let's say, to a sum s. Then we know that s is integrable. And we know that the integral of Sn should converge to the integral of S. But the integral of Sn is the integral of the sum, finite sum. By the linearity, we know that the sum of the integrals, right, converges to the integral of S as well. Hence, we have the following property. We call this property as a term-by-term integration. Generally, if you have a sum of a finite number of integrable function, we know that you can integrate the sum by adding up the integral of each part. Generally, for an infinite series of functions, that might not hold unless uniform convergence of the infinite series is guaranteed. This is why uniform convergence is important to mathematicians who studies analysis. So to state it formally, if each fn is integrable in the interval ab, and we know that the sum converges uniformly on the interval ab to a certain function, which we will not name, then we know that the sum, whatever that sum is going to be integrable in AB. Furthermore, the integral of the infinite sum is the infinite sum of the integral. So you can integrate term by term, and that can be guaranteed as long as the series converges uniformly. So this is one advantage of a series converging uniformly on an interval. Another property where uniform convergence can be applied is when we talk about the limit of a derivative of a sequence of differentiable functions. When can we say that the limit of the derivative is the derivative of the limit? We illustrated that this property is not necessarily true unless these properties must hold. Now, it's a little bit complicated, so if you have more time, you can review our previous video lesson about this theorem. It says that if each of fn is differentiable on an interval I here is an interval, and that for some point x0 in I, the sequence of numbers fn of x0 converges as n approaches infinity, meaning to say this sequence converges for at least one point in I. Now, because each one of this is differentiable, each one has a derivative. If each derivative is continuous on I, and the sequence of derivatives converges uniformly to some function on I, then we can say that actually fn does not converge on at a certain point only. Now, we can guarantee that f sub n actually converges pointwise to some function f on I. Furthermore, this function f is actually differentiable and its derivative is g. Meaning to say, g is precisely f prime, so that the limit of the derivative is equal to the derivative of the limit. If we apply this to the sequence of partial sums of an infinite series of functions, differentiable functions, we get a property called as the term-by-term differentiation. In other words, if you have a sequence of differentiable functions on an interval I, and that this series converges for at least one x not in I, then if the sum of the derivatives converges uniformly on I to a certain function, then actually the series converges pointwise, the original series converges pointwise on I to a sum which is a differentiable function. Let me correct this. Then this series converges pointwise on I to some this is some differentiable function. Furthermore, the derivative of the sum is equal to the sum of the derivatives. Now we shall illustrate this shortly. So for example, you can consider the infinite geometric series which is valid in this interval. Remember that the convergence is uniform on each of these for all r between 0 and 1. Now, because this interval is symmetric about the origin, meaning to say, if x is in here, then you can expect that minus x is still here. Hence, the equation is still valid if I replace x by minus x. Now, the equality becomes the following. So here, x will be replaced by minus x quantity squared will be equal to x squared, and so on. So you get now an alternating sign. Also, it can now be guaranteed also that this series is actually uniformly convergent on this interval as well. Hence, it's uniformly convergent on half of the interval from 0 to r. If we apply term-by-term integration over this interval, we get the integral of this from 0 to r, and then you integrate each one of the term from 0 to r, you get the following equality. On the left-hand side, using calculus, you can verify that that's ln of 1 plus r, while this one evaluates to r, this one evaluates to r squared over 2, this one evaluates to r cubed over 3, and so on. And we get the following infinite series, which is valid for all r between 0 and 1. Taking the limit of both sides as r approaches 1, we get the following equation. ln of 2 equals 1 minus 1/2 plus 1/3 minus 1/4 plus and so on, which is precisely our alternating harmonic series. So right now, we have given a proof that the alternating harmonic series actually converges to ln of 2. And actually, if you calculate the ln of 2 using our calculator, you can see that ln of 2 is right around 0.6931. If my calculator is correct, this is around 0.6931. Okay. Now, instead of replacing x by minus x, we could also replace x by x squared. Because if x is between -1 and 1, x squared is still included in that interval, so therefore we could replace x by x squared in our equation, which will give us the following. This is true, and the convergence can be shown to be uniform as well in this interval for all r between 0 and 1. Again, if we integrate both sides from 0 to r, we get the following. But instead, the integral on the left-hand side, as per your calculus, evaluates the arctangent of r. And each one of these evaluates to a certain powers of r. Hence, this is valid for all r between 0 and 1. Taking the limit as r approaches 1 from the left, we get the arctangent of 1 is pi over 4, and each one of these evaluates to 1 minus 1/3 plus 1/5 minus 1 over 7. So basically, this is the alternating series of reciprocals of odd integers. If you add all of this, you get a sum equal to pi over 4. Or you might as well write it as pi equals, if you multiply 4 on both sides, you get the following. You get now a series approximation or a series expansion for the number pi. So as you can see, pi is an infinite sum, or is a sum of an infinite collection of rational numbers. One of the most celebrated and actually the most famous examples of a series of functions is that of a power series. A power series is just a series of functions where each term is actually some power of x. That's why the name power series. But actually, what I'm talking about is a power series with c equal to 0. So as you can see here, so you can think about a power series as an infinite polynomial, if I may call it that. In general, you could change the value of c to something else and get the following expression. In this case, we say that c is the center of the power series. Now, the most important part of a power series is not the center, but actually the coefficients a sub n, because a sub n here can be replaced by any sequence of real numbers. So our next question is that, and why are power series important, and why are they celebrated? Well, the answer is because they are mostly well behaved. No? As you can see, or as we shall ask in the following question, for what values of x is the power series convergent? As you will see, the set of all x in which this series converges is quite special, as the following theorem reveals. So let's say a sub n is the sequence of coefficients. As you will see, the set of all x in which the power series converges is only determined, or is only dependent on the sequence of coefficients, and it's not really dependent on where the center is. So here, you first calculate the number rho, where rho is the limit of the nth root of the absolute value of an. Now this might look familiar because it is in fact indeed a consequence of the root test. Now, because the root test is applicable only to series with non-negative terms, we put an absolute value over here. So here, if we calculate this limit, and this limit is found to be positive but not infinite, then we can say that the power series converges absolutely on all x satisfying this inequality, meaning to say at all x whose distance from c is less than the number r. What is that big R? This big R is basically the reciprocal of this number. So let's say you get a number here and the number was 1/2. Okay, so you get here 1/2. So big R should be a 2, meaning to say within a distance of 2 units from C, the power series will converge. In fact, beyond 2, the power series will diverge. In fact, the convergence is absolute. Okay? If this rho calculates to 0, let's say, then we can conclude that the power series converges absolutely for all x in R in the entire real number line. If this rho calculates to infinity, then this power series converges only when x is C. In that case, this series has a sum equal to the first term a sub 0. Before I continue, let me apologize for the unnecessary noises because there is a ongoing construction above me. Alright, so if rho is 0, as you can see in number 1, we simply let big R to be 1 over rho, or the reciprocal of rho. If rho is 0, we simply set r to be infinity. So parang isipin nyo parang reciprocal kasi ng 0 infinity. And it's not real that. You can just define. On the other hand, if rho is infinity, we just set big R to be 0. We then call R the radius of convergence. Why is it the radius of convergence? Kasi as you can tell, like in number 1, no, if this is C plus R, this is C minus R. Within this open interval, there's the series converges. But outside that interval, or beyond that interval, the series will diverge. So that R determines the radius, or 1/2 the diameter. That's why it's called the radius of convergence. So that's why we set R to be infinity, because in number 2, if rho is 0, this series converges everywhere, so we might as well say that the radius is infinity. If rho is infinity, the series converges only at the center, so we might as well want to say that the radius is 0. Now, the set of all x in which the power series converges is what we call as the interval of convergence. So, for those who are kind of quick, might already question, how about, sir, at the points where x is at the boundary, c minus r and c plus r? Well, this theorem doesn't have any conclusion, so you have to test it one by one. So, for the proof, you just apply the root test for number 1. So, assume rho, what's rho again? It's the limit of the nth root of the absolute value of an. Note that, by the way, assuming that rho is between 0 and infinity, note that I took the nth root of the nth term of the power series, and then I let the limit as n approaches infinity. See, yung mawala yung nth root wala yung nth power nito, mawala siya, di ba? Kakunin yung nth root, matitira na lang absolute value of c. And then, yung limit ng nth root ng absolute an is being rho. Sa root test, ito yung number na kailangan mong tingnan. If this is less than 1, convergent. If this is more than 1, divergent. So, by the root test, this converges if and only if this number is less than 1. But may absolute value kasi nga may absolute value ito. And must diverge if rho times absolute x minus is greater than 1. This implies that this converges absolutely kasi nag-converge yung may square root within this interval and diverges outside that interval. And then, the proofs for number 2 and number 3 are left as exercises. So, for a clearer diagram, this is what happens in the first case. Here, you get a finite positive radius r. So, in this interval, convergence is guaranteed. In these intervals, divergence is what will happen. As you can see, I put a black hole here, no, to indicate that we don't have any conclusion at those points. You have to check it one by one. Yun nga, sabi ko, the theorem is inconclusive in the case when x is c plus or minus r. In fact, we can say that r depends on a sub n alone and is independent of the center, because in getting the radius, we only need to get the an. C does not have any role in calculating the radius r. In fact, r can be calculated as 1 over the lim sup, or the limit. Huwag na lim sup, limit na lang. Ito yung magsasabi kung ano yung radius of convergence. Ito kasi yung rho, if you can remember. Okay? So, for example, let's determine the interval of convergence of the following power series. Now, in order to answer this, let's first rewrite this power series in standard form, where you can see a sub n and you can see the center. Right now, it's not yet in that form, no? But as you can see, I can actually factor 2 here, 2 to the n, x minus 3 halves to the n over n times 5 raised to n. So there, you get that a sub n is what? 2 to the n over n times 5 to the n, whereas the center C is the number 3 halves. Now, what is the radius? We first calculate the rho. Mamaya, kunin natin yung reciprocal. The rho is the limit as n approaches infinity ng nth root ng absolute value an, just in case may negative terms ka, no? Kukunin mo yung nth root nito ngayon, ang maiiwanan, wala na absolute value kasi positive naman lahat. Sorry, n times 5 to the n, you get limit, bali magiging 2 over 5 n raised to 1 over n. Naalala nyo yung n raised to 1 over n? Ano sabi ko tungkol doon? Ang limit niya ay 1. Kaya ito ay 2/5. Right? 2/5. And therefore, what is the radius? Because 2/5 is positive and finite, it's just the reciprocal. So, the radius of convergence is 1/2. Meaning to say, if the interval of convergence is I, this means that I is found, the center is at 3 halves. Magsusubtract ako ng 5 halves, magdadagdag ako ng 5 halves. Tapos dito i-close to. Anong ibig sabihin nito? Ang ibig sabihin nito, so let me finish the calculation first. This is negative 1 up to 8 over 2 is 4. Tama ba ako? 4. Is this correct? Yeah. Alright. So, ganito yan. The interval of convergence, well, it contains, we already know that it contains the entire open interval. But it is contained in the closed interval. So, in other words, the interval may or may not contain negative 1 and 4. So, how would we know? We test it 1 by 1. So, at the boundaries, if x is, well, let's say, if x is negative 1, ano mangyari sa power series mo? If x is negative 1, this leads to negative 1, so magiging negative 5 raised to n over n, 5 raised to n. May iwanan na lang, bale, negative 1 to the n na lang over n. Pag ito in-expand mo, parang ano lang to, ito yung negative 1 plus 1/2, alternating harmonic, pero may negative times negative 1. So, parang ano to, negative ln of 2 ang sum. Kaya alam natin na ito ay convergent. Right? Kung sakali naman ang x ay, let's say, ano yung isang endpoint? 4. Saan naman maglilid itong sum na ito? Paki-calculate. Saan equal to? Mag-equal naman siya sa 1 over n na lang, which is divergent. Diba? Therefore, the interval includes negative 1 but not 4. So, the interval of convergence is the closed negative 1 for open. Do you get what I'm trying to say? Okay. So, the next question is, pag ikaw ay may power series, saan siya nagko-converge uniformly, or in what portion of the interval of convergence is it uniformly convergent? You know why uniform convergence is important? Recall muna tayo. Ang absolute convergence ay important just in case you wanted to rearrange the terms. So, in other words, in terms of algebra, good na ang series mo ay absolutely convergent. But in terms of calculus, if you want to integrate term by term, you want to differentiate term by term, then uniform convergence is a must. So, in which part of the interval of convergence is the convergence uniform? So, here we get a hint. If r is positive, And it is the radius of convergence of the series. So, hindi kasama yung mga series with 0 na radius of convergence. Actually, kasama dito yung case when R is infinity. If K is a subset of this open interval and it is compact, no? Isabihin ng compact. Well, mahaba ang definition nito. Yung if every open cover has a finite subcover, no? But because we are in the real number line, the Inequality theorem simplifies the definition into sa real number line, ang mga compact sets ay mga closed at bounded. So, kung si K daw ay closed at bounded na subset ng C minus R, C plus R, then on that, the series or the power series converges uniformly. Now, one important property of a compact set is the fact that if you get a continuous function whose domain is compact, it always achieves a maximum and a minimum value. Ang tawag natin dun ay extreme value theorem. Pinuunang i-apply natin. So, si K ay compact. If you look at this function, this is just a continuous function. Ang shape yan, parang, kung i-drawing mo yan, parang ganito. Yan, ito ay C, no? So, let's say, ito yung K. Yung K mo ay closed at bounded. On this interval, it has both a maximum, in fact, ang maximum niya nandito, ang minimum niya ay 0. Right? Pero hindi kailangan yung minimum. Kailangan lang natin ay maximum. Kunwari, nangyayari yung maximum doon sa x0. Okay? Siyempre, yung x0 na yun ay hindi C kasi at C, nandun yung vertex nung nung graph na ito. Observe that if I take the absolute value of this, I can rearrange it as follows. No? Ito yung original. Ito, tsaka ito. Yan yung original. Ako nag-insert ako ng factor na ganito, pero dinivide ko rin para mag-cancel. Okay? Now, ano ba to? X0 is not C, so very good. This is not 0. Can always do this, right? The thing is, because ito yung maximum value na ito, kung ano man ito, mas maliit ito dito. Right? So, this expression is less than 1. Sabihin natin, less than or equal to 1 to be safe. Kaya ito ay less than or equal sa absolute AN times absolute X0 minus C raised to N. Alright? Tawagin natin ito ngayong M sub N because this is now independent of X. X0 is just a constant. Dahil yung X0 ay nasa K at yung K na yan ay nasa loob ng interval of convergence, then the sum of this is guaranteed. Kasi nga sa loob na ito, di ba, ang convergence ay absolute. So, ito ay convergent. Hence, by the Weierstrass M test, you can now say that this converges uniformly on K. That's why the Weierstrass M test is really important. Some books call this as the Cauchy-Hadamard theorem. I don't know kung meron ba siyang standard na name. Pero ito'y fact. Ano ngayon ang mga consequences? Ito yun. So again, kunwari ito ay may positive na radius of convergence. Okay? So unang consequence, dahil lahat ito ay polynomials lang, ang convergence ay uniform sa lahat ng closed interval subset na ito. So mangyayari, continuous siya. Continuous kasi lahat ng mga di ba? In fact, continuity implies integrability. So, kung meron kang closed interval sa loob na ito, you can always integrate term by term basta nag-integrate ka sa loob ng interval na ito. Kaya na lang bahala mag-evaluate ng integral yan. That can be evaluated. Also, you can differentiate term by term as long as dito ka sa loob na ito. Ano bang derivative? Scratch muna tayo, ha? Ganito yan eh. Ang unang term, bale, well, f of x natin ay a0, a1, x minus c, a2, x minus c squared, plus and so on. Ano yung first derivative? a1, 2a2, x minus c. Ang kadugtong yan, 3a3, x minus c squared, plus and so on. What results is another power series. Ito siya pag in-expand nyo. In fact, same ang radius of convergence kasi tingnan nyo yung an. Ang an nyo dito ay, ang bago nyong an ay ito. Pag kinuha mo yung nth root nyan, makikita nyo parang nth root of n times nth root of absolute an. If you take the limit as n approaches infinity, 1 lang kasi ito. So, kung ano man yung radius na no original, yun din yung radius ng derivative. Hindi lumiliit, hindi lumalaki. Now, let's go back. So, dahil power series ulit ito, the same theorem can be applied here. So, in fact, hindi lang first derivative ang meron. Meron ka rin second derivative, no? Tsura ng second derivative ay 2a2 plus 3 times 2a3. Hindi ko multiply. Plus 4 times 3a4 x minus c squared and so on. If I take the third derivative, kunin natin hanggang fourth. So you can see the pattern. 3 times 2 times a3 plus 4 times 3 times 2 a4 x minus c. Ang susunod dyan, 5 times 4 times 3 a5. So what I'm really doing is induction. Fourth derivative, you get 4 factorial, di ba? a4 plus what? 5, oh, sorry. Yeah, 5 times 4 times 3 times 2, a5, x minus c, and so on. I don't like to continue. As you can see, if each one of this is evaluated at c, a0 na lang ito. Kung yung first derivative in-evaluate sa c, a1. Second derivative in-evaluate sa c, 2a2. Third derivative in-evaluate sa c, 3 factorial a3. In fact, fourth derivative when you evaluate it at c, 4 factorial a4. So may pattern. What is that pattern? Ito yun. Actually, f is infinitely differentiable in this interval. In particular, for each n, the n derivative at the center, this should be c, not x naught. Narito na ako. This is c. Is n factorial times a sub n. Okay? So actually, a sub n can be rewritten, no? A sub n can be rewritten as what? What? Can be rewritten as the n derivative at c divided by n factorial. So may relationship yung mga coefficient sa n derivative at c. So the coefficients actually tells you kung gaano kalaki yung mga n derivative. Remember, you can always differentiate a power series any number of times. These derivatives can always be guaranteed to exist no matter how many times. Kaya ang sinasabi natin, a function represented by a power series is what? What? Infinitely differentiable. Infinitely smooth. Some authors call it that way. No? Kaya nga kapag si f ay equal, kailangan equal ha. If this is assumed to be equal, no? As a consequence, magagaranti, okay? Magagaranti natin ng f of x can be written this way. Sorry sa ingay ha. Ito yung tinatawag na Taylor series expansion ni f. In this case, equal ito. Ang tanong natin dyan, paano ko si f of x ay hindi natin alam ito, for example. I mean, we don't assume this. So you get a function, an infinitely differentiable function, and then you construct the series, for example. The question is, does this converge to f, or is this equal to f? Parang somehow, parang pabalik. Sagot ay hindi, palagi. Pero let's not talk about that anymore. Another consequence is the uniqueness theorem. No? So let's say, meron kang another power series, same center, but different coefficients. Let's say an and bn. Assuming that these values, the values of f and g, equal at or in this interval, for all x in this interval, same radius. No? Actually, an is nothing but mangyari si bn ay equal lang naman daw sa an. So in other words, if there is a power series representation for f of x centered at c, then there is a unique set of, or there's a unique sequence an, so that f of x is equal to this. Kasi kung meron mang iba na equal pa sa f of x, yung coefficients daw nun equal lang daw dun sa original. Okay, that's the idea. After this lesson, problem set is already coming up. Please wait for it. Okay, see you next time.